Swayam Prabha. Digital India. Educated India.
New topic on the furrow irrigation system. We will look into the details of the furrow irrigation system, the design aspects, the various design parameters which are required for the detailed design. But before we do that, I would like to establish a relationship between the various elements which are advance time, infiltration, and deep percolation. This relationship will be a general purpose relationship which will be used for all these surface irrigation methods. Even the border irrigation method which we have considered earlier, this will be applicable to that. This will give you a general understanding that how these items, the advance time, the infiltration and the deep percolation are related to each other, and these relationships you can exploit for the design purposes. So this will be a very important way of looking at the overall process. Let's take the Kostyakov relationship. Which we had defined earlier, and this gives the infiltration depth, the accumulated infiltration depth with respect to the opportunity time and these two parameters which we had defined. C and alpha are the empirical constants or these parameters. We had also seen that how we can derive these parameters from the observed infiltration data which is taken in the field. So these are basically defining the type of soil. For each type of soil, these parameters are known. And T is nothing but is the infiltration opportunity time. In other words, if I write T, I can write this T in terms of y and these two parameters. I can approximate this T, which is the infiltration opportunity time, to this T here, as we have used, this T is nothing but infiltration opportunity time. Which means that at the surface of the the ground, for how long the water was available and for how long the infiltration opportunity was prevailing. So accordingly, the depth of infiltration can be determined depending on what is the time of infiltration, or what is the time for which at least that assumption is valid, that the amount of water is more than the infiltration opportunity or the infiltration capacity. Those things we have seen, and since in irrigation, when we are applying the irrigation water, we are ensuring that the depth of irrigation is always more than the infiltration opportunity or the infiltration capacity prevailing at that particular time. But we can make an approximation that this time can be approximated to the time of irrigation. So when we find out this time, the t now may be taken as the required time of irrigation. What assumption we are making is that the time of infiltration opportunity is equal to the time of irrigation. So indirectly we can find out that time if we know the characteristics of the soil. This relationship is known, which we have already looked at. Now let's assume that the soil is, we make two more assumptions. First, the soil is uniform. That means the soil characteristics are not changing for that particular field which is in question. And we also make another assumption that the initial moisture content is also uniform. Now making these two assumptions, let's take that the distance z, we take z as the vertical distance, the distance z from the soil surface to the depth of wetting when you irrigate the soil, when the infiltration will take place, the wetting front will move. So if you want to express that wetting front in the form of distance z, then this distance z can also be expressed. It can be expressed as a function of y. Okay. That will be proportional to, with some proportionality constant. If k I define as a proportionality constant, if k is then I can express z with respect to y, and if I substitute y from the Kostyakov equation, this can be expressed as plus Ct to the power alpha into k. Now these are two constants. I can express this as a new constant which is k dash t to the power alpha. Okay. Let's take two more quantities. Tt as time required for advanced curve end of the field. Time required for advanced curve to reach the end of the field, and if Tn is the time required to infiltrate the net irrigation requirement, which is Yn. So, to achieve the net irrigation requirement, if you need the time Tn, that is the time which is required to get this net depth of irrigation, and Tt is the time of advance of the waterfront to reach the downstream end. Now, here comes the various options available to you. It depends on your type of soil as well as the length of the field, that what will be the value of T in terms of Tn, or what is the proportion of Tt of Tn which is required for the waterfront to move in the downstream direction and to reach the downstream end of the field. For example, right now we'll assume that, we'll make assumption, we'll take one case where we will assume that this Tt is 1/4 the time of net infiltration. That if your net infiltration is 1 unit, it will take 1/4 the time for the advance curve to reach the downstream end. So, if we make that assumption, there can be various cases. It depends on the characteristics of the soil, it depends on the length of the field, that what will be the Tt, because the movement is a function of how much of the water is infiltrating into the soil as the water is moving in the forward direction, and is also a function of what is the length of the field. So, this is only one possibility. There can be many possibilities depending on how you have fixed the other parameters. So, let us make assumption that we are making assumption that Tt for the present case which we are going to consider is 1/4 the Tn. The time taken for the net irrigation depth to be achieved is 4 times the time taken for the advance curve to reach the downstream end. So, with this assumption, we divide the total time taken, which is the Tn, into 4 different parts in such a way that delta T1, each one of these are the various intervals which we are going to consider, and each one is equal to Tn by 4. Okay. Let us try to have a look what we have done so far. I will try to sketch this, that this is your total field. This is the upstream end, the downstream end. Okay. I say that this is the root zone depth. Which you are interested in irrigating. Fine. And this root zone depth, the total time taken, you are divided in, when you are trying to consider what will happen each time interval, which you have considered, each one is equal to 1/4 the total time requirement. So if that is the case, let us look at that what will be the depth of water infiltrated in the first time interval. The first time interval is delta T1. Depth of infiltration is, if I say that in general the depth of infiltration, if you want to take in any one interval, it will be a function of what is the initial depth in the soil and what is the depth infiltrated during this time interval. So if yi is the infiltration during that or at the end of the interval, and y naught is the infiltration which was already available in the beginning, then during that interval you have the increment depth interval, the depth of infiltration is delta yi. So similarly, the depth of soil which will become wet, which we will call as delta Z1, you can write, because we are saying that this is our total Z, this root zone is the Z which we are considered, this is the total depth. So in the first interval, this will be the depth of soil which will be wetted in the very first interval. If we assume that Z0 to start with, let us make an assumption that Z0 is 0 to start with. If it is known, you can take that value, but if it is not known, then if it was totally dry, you can always take it to be 0. Not a very appropriate assumption. So once you assume this, you also need the value of alpha to be used in that equation, the Kostikov equation. Let us assume that the value of alpha is also known. Just for the present problem, let us take this to be 0.5. Then if these two things are known, then the very first interval delta T1, you can write this delta Z1 is equal to Z2 minus, sorry, Z1 minus Z0, and Z1 is nothing but, you have said that 0.5 minus 0 in this present case, which is nothing but Z1. Okay. So in this particular case, if this is delta Z1, I can similarly write the expressions for other intervals for delta T2 time interval. I can find out what will be delta Z2 as Z2 minus Z1. Okay. Now Z1 is nothing but this much depth, isn't it? This is Z1 is equal to delta Z1. So to find out the next depth, I am trying to reduce this Z2 minus the previous depth which has been considered earlier in the previous interval. So Z2 minus Z1, which will be equal to K dash into T2 to the power 0.5 minus delta Z1, because Z1 is equal to delta Z1. Now T2 is two times T1. Okay. So if you substitute that, your Z2 will be K dash into T1 to the power 0.5 into 2 to the power 0.5 minus delta Z1, which is nothing but delta Z1, this part is delta Z1 into 2 to the power 0.5 minus 1. Okay. Similarly, you can write the other forms also. Delta Z3 will be delta Z1 into 3 to the power 0.5 minus 2 to the power 0.5 and so on. Delta Z5 will be 5 to the power 0.5 minus 4 to the power 0.5. So this general relationship can be established, and if we plot this onto this, you will find that at the end of t is equal to 1, this will be the general trend. If we take that this is a linear variation, you can find that over the length of the field, this will be the variation which will be encountered because of the fact that the water is moving from the upstream end to the downstream end, and the water is taking 1/4 the time. Since the time is equal to the time to reach the downstream end, when the water will reach just the downstream end, the infiltration will be minimum there. Similarly, the other segments, you will find that the size of the segment, the depth of infiltration will keep on reducing. That is what you will see in the relationship, and in each case this will be the trend of the infiltration for each of the smaller segment. For example, this is for t is equal to 2, t is equal to 3, t is equal to 4, and if you go beyond this, take another segment, you will find that in this is for t is equal to 5, though you have gone beyond the root zone depth. Now these equations, if you just analyze these equations, you will find that this trend will be shown. Each successive z or delta z which is lower down will be having smaller and smaller depth, and that is quite understandable because we have been studying this so far, that what happens when you go when you have the infiltration for a longer period. So that is what is reflected here, that the initial infiltration will be at a higher rate, the later infiltration will be at a lower rate. Now if you want to satisfy the downstream end of the field also, you will have to provide the water beyond this root zone depth. That means for an additional time period. Only then this component, the lower part of the field, can also be satisfied. Or in other words, what you can say is that if you want to satisfy the needs of the downstream end also, you have to ensure that at least the water should be available there for Tn time. What is the net time for which the infiltration should take place, so that to achieve the net irrigation requirement. Okay. So that is what you can write in the form that to infiltrate depth yn into the lower end of the field, there should be opportunity time at the lower end also equal to Tn. Okay. But we also know that T4 is equal to how much? 4 times T1, and correspondingly Z4 is K dash 4T1 or delta Z1 into 4 to the power 0.5, the same thing. So to achieve this, the infiltration opportunity in order to achieve this requirement, the opportunity time at the upstream end has to be T5, which is equal to Tn plus Tn by 4, or is also equal to 5 times T1. and the corresponding Z5 is delta Z1 into 5 to the power 0.5, as we have done here, the same thing. Okay. Now, if that is what we have plotted here also, this is basically the same thing which we have plotted, that if you want what will happen at t is equal to 5, so that is what we have plotted already here. Now, we will define two quantities which are very important quantities for our subsequent analysis and the design purpose. We can utilize these. The first is that if you want to know the average depth of soil which has been wet by deep percolation, what will be the average depth of soil? Is basically this part, this portion which I can mark here. This is the deep percolation which could have been avoided, but since we wanted to take care of the downstream areas, we have indulged in this deep percolation. So this deep percolation if you want to know that how much deep percolation you have indulged into, you can express that as delta Z5 by, that is the average deep percolation. Delta 5 is the maximum deep percolation. If we assume that this relationship is linear and is varying from delta 5 on the upstream end to the 0 level at the downstream end, then we can say the average deep percolation is delta 5 by 2, which can also be written as Z5 minus Z4 by 2, because delta 5 is nothing but Z5 is the absolute value or the total depth up to that level, and Z4 is the depth up to the root zone level at the upstream end. Let me say that this is delta Z2, the next one is delta Z3, this is delta Z4 and delta Z5. Okay, these are the individual values, but for each one this is the Z1 up to this, up to the next one is Z2, Z3, Z4 and Z5. So you can use it either way. This is Z5 minus Z4, that is what is delta Z5 by 2, that is also you can write. So this in fact is nothing but, you can write as this in the general form, minus 4 to the power 0.5 into delta Z1 by 2. Okay, this is one which gives you that what is the average deep percolation, and if you want to find out the average depth of soil, which has been wet, then you can express that as Z4 plus Z5 by 2. So the total depth which has been wet, what is the average value of that? Is the average of the two extremes. On one side is Z5, other side is Z4. So So the average of that will give you the total depth which has been wet. This you can also express as 4 to the point 5 plus 5 to the power of okay. Now if you take the ratio of these two quantities, the ratio of average depth of deep percolation to average depth of wet soil you can write this as Z delta Z5 by 2 by Z4 plus Z5 by 2, which is 5 to the power 0.5 minus 4 to the power 0.5 by 5 to the power 0.5 plus 4 to the power 0.5, and Z delta Z1 is cancelled out. So this is the ratio which is in this particular case is 0.056. Now in this specific case, what it amounts to is, you can now formulate that if the time of advance Tt is 1/4 the Tn is 1/4 the net infiltration time Tn, and for a alpha of 0.5 the average depth of deep percolation is 5.6%. Okay, this is only one instance which has been analyzed. Similarly, there are many other instances which have been analyzed by taking different values of alpha, which means that by taking different characteristics of the soil and by taking different FAR ratios, which is the fractional advance ratio. This ratio Tt by Tn, we call it as FAR or fractional advance ratio. So if these are known, then you can formulate the relationships which can be used subsequently for your analysis, and I'll show you some values of the table which have been which has been provided through the similar analysis which we have done just now. This table looks like this. I'll just pick up some of the values out of this table so that you can get a feel of this table. Gives the expected percentage of deep percolation, and on this side you have the fractional advance ratio FAR, here you have the alpha values for different soils, maybe ranging from 0.1 to 0.9. For a FAR ratio of 1, or you can write it as T, that means the time of opportunity is same as the time taken by the advance curve to reach the downstream end. You will have the values you can look at the order of magnitude of these values, that how much, if you have this parameter fixed in such a way that your advance curve, or the time taken to reach for the advance curve to reach the downstream end, is equal to the opportunity time requirement for the net infiltration to take place, you will incur a lot of losses, and those losses will also vary from soil to soil. The soil is a function of alpha, so if your alpha is increasing, the deep percolation losses are also increasing. Let's take another sample of when you have T by 4, out of which we have analyzed only one, but for the others, for example, when alpha is 0.1 and you have a FAR ratio of T by 4, in this particular case, the deep percolation losses will be 1.1%, 2.2%, 3.3, 4.5, 5.6. That is what we have analyzed for alpha is equal to 0.5, and for FAR ratio of T by 4 or 1 by 4, and 6.7, 7.8, 0.9 and 10%. Let's take the other extreme of T by 10. That means you are flooding the total length in a very short period. That's where FAR ratio is T by 10. So in this particular case, your deep percolation losses will be still smaller. So this table now can be utilized for picking up some of the parameters. You can find out that if you want to accept only the deep percolation losses of a specific range, you don't want the deep percolation losses to be more than 10% or more than 5%, and you know what is the type of soil which is the prevailing type of soil, you can pick up that alpha and you can find out what is the most preferable FAR ratio which can be utilized, and that can give you some indication towards what should be the time of irrigation should be selected, and what will be the time of accordingly the time of infiltration which will be available is not dependent on only these things. It will also be dependent on then which stream size you will be picking up. What are the other parameters of the field? What is the grade? All those things we have not considered so far. This is only the starting, those parameters which are independent of the other aspects of the field. They are only giving you the relationship between the soil type, which is through alpha, and the advance time, which is again dependent on the soil type to a certain extent. And all these relationships can be utilized to start your design considerations, looking at which are the most suitable parameters which you should start with. Okay. So this analysis is, as I had mentioned in the beginning, that this is not only concerned with the furrow irrigation. It is as a general purpose analysis which can be made use of in all the surface irrigation methods. Next we'll try to now start looking at the furrow irrigation method in particular. First of all, we'll try to look at those relationships which are obtained through experience, through field trials. So these relationships which are based on and field trials, these relationships are very important in the absence of detailed data, because you can also use the hydraulic relationships which are more exact, but many a times you will find that the required data is not available. So you have to start at least looking at the designs with some indicators which are available. And since it's a very important area all over the world, there are world organizations like FAO which have compiled this information and made it available in many reports, where is easily available, where people have come out with under different conditions what will be the limiting design parameters from various considerations. And we have already considered in the case of border irrigation also that the major considerations are of the things like that the stream sizes shouldn't be erosive, you shouldn't create problems for your fields. Then there is one consideration, the other is that your efficiencies should be reasonable efficiencies. So that will be basically dictated by what sizes you will choose. Will be the combination of discharge, the stream size, the size of the field with respect to the soil type and with respect to the slopes, the prevailing grades. When you look at the grades, there again you have to look at, are those grades excessive, which can create problems of erosion? Are those grades very flat, which can also create problems of the drainage? So there are no specific rules and regulations which are applicable all over the places. You will have to look at the climate, you will have to look at, is it a humid area, is it a arid area? The rules will be different for the similar soils, but if the area is humid on one extreme, on the other extreme if the area is arid, you might have to choose different parameters. For example, let's assume that if it is a humid area. Now in the case of humid areas, you will have a lot of rainfall occurring, and that too the intensity of the rainfall will be very high. if you go in for slopes which are steep slopes, maybe that during the irrigation time you can control those stream sizes, you can control the rate of application of water, but what will happen when the rain will occur? There won't be any control. At that time, the slopes which are prevailing in the fields, they will remain there. So when the rain water will be generated, the surface runoff will be generated, that will create havoc. That will create a lot of erosion, and all your fields might be distorted. It might be devoid of all the fertile land which was there. It might damage the crop altogether. So all those things are possible. So when you look at those recommended parameters, you will have to take into consideration many other conditions which are beyond the irrigation conditions. These things are very important, and we'll look at all these relationships which have been formulated on the basis of the experience of the farmer, because the farmer might not be having the scientific explanations of all these practices which he has been indulging into, but through the experience, through the common sense, he has arrived at some of the combinations which are very scientific, which are very realistic, and those things have also been taken into consideration when the various researchers have looked into all these various possible details of these parameters, and they have taken into confidence or into consideration all those experiences of the local farmers, and those have also been brought out in all those publications wherever possible. Along with that, the other recommendations are based on the experimentation, which for example in the case of border irrigation we had seen that how we can do the evaluation runs. So through those evaluation runs you keep on taking the observations, and then you analyze those data and come out with the recommended procedures. For example, in the case of the erosion, you run those stream sizes in the fields and see that how much erosion is taking place. You find out which are the stream sizes which are limiting stream sizes, beyond which if you increase the stream size for those specific type of soils under those slopes, you will have the erosion problem. So that is how you collect the data and you make the recommendations. So all those things we'll discuss in the next class, and along with that we'll also look at the hydraulic relationships which have been formulated on the basis of the hydraulic principles, and they can be used for the design wherever those data, the required data are available. Okay. Any question at this stage? Thank you then.